Whoop. Somehow it's not moving. Now it's moving. Okay, perfect. So yeah, let me first thank the organizers for making such a nice conference, especially this. I appreciate this non-equilibrium part of it. And I really learned a lot in the last days. But today I would like to introduce a new protocol, basically to address a very old question, which is this chicken and egg question, where we are having several competing degrees of freedom in our system, and we would like to understand which of them is the driving force behind a given phase transition. And the idea is based on changes in the lifetime, so photo-induced changes in the lifetime, and the data can serve as a very sensitive measure of underlying microscopic competitions. So the setup, which I imagine, it's actually very simple. We're having an insulator, which we photoexcite between the lower, between the conduction and the valence band, somehow resonantly. And first we expect that highly excited electrons will cool down to the lower edge of the conducting band. So we have some kind of a cooling dynamics, and there's a time scale separation between this cooling dynamics and the thermalization, when the charge carriers has to recombine slowly across the gap, what we heard in the previous talk, right? And now I want to focus on this state, so the cooled state, and ask how are the properties of quasi-particle changed after the photoexcitation. And I'll show you on the two examples that if we focus on the changes in the lifetime, we can learn a lot about microscopic interactions. So most of my talk, I will talk about this material called tantalum-2 nickel selenium 5, which is a correlated insulator. And there's a long debate if the insulating state is originating from excitonic or lattice degrees of freedom. And in the second part, since we are in the photodoped mod case, I'll show you something how we can apply the same idea on cuprates. Good. So, but let's return back. What is the basic idea of lifetime of charge carrier? So if you remember your textbook lessons on Fermi liquid, basically I put an electron close to the Fermi surface, and it's a phase space argument which basically allows him that he cannot, which prevents him to scatter. And this is why basically quasi-particle, it's a well-defined particle, right? And similar we can argue for large gap insulators. And the basic question which I want to address today, how does this textbook picture changes after in a photo-excited state? So show you, I said, two examples. The first one is tantalum-2 nickel selenium 5. So let's just introduce the material. It's such a transition metal chalcogenide. It's a layered material composed of such a chains. And there has been various like transport properties or thermodynamic properties which are showing that there is a phase transition happening. See, there's some anomaly here in the specific heat at well above 300 Kelvin. Yeah? And the real so why people first start to connect this with some kind of excitonic transition, it was this ARPES data. So at low temperature, you're seeing there's a very flat band, very flat band close to the center of the brilliant zone, and there is a strong kink here. So this is a typical signature of an excitonic transition at excitonic insulator at K0. However, in the actual material, we are having an electronic transition coupled with a structural phase transition. So we are going basically from this orthorhombic to monoclinic phase. There is some kind of a soft shearing mode, which is happening between the chains. And now this is a typical chicken and egg problem. In a sense, we're having in the ground state two coupled order parameters. They're intertwined. So how are we gonna separate the two? And the question at the end boils down to which of the interaction is the dominant one, right? If we can address this ratio between the Coulomb interaction, which is responsible for the excitonic pairing, and the electron-phonon interaction, which I mark here with lambda, and if we can somehow quantify the ratio, which of them is the dominant, we have an insight of what is the driving mechanism. And I'll be solving such a problem where basically the band structure, it's encoded it's taken from the DFT calculation, and I this is the corresponds to the Coulomb interband Coulomb interaction, and this is the electron Folman part. So, what was the previous mindset in the field of photodope insulators? So basically, idea it goes something like this: I photoexcite the system. I check how fast does the gap evolve, right? And if the gap closes on the time scale, which are much faster than lattice time scale, then this has to be electronically driven transition, or vice versa. And now, this was exactly what was done first by Okazaki et al. On the left, it's the equilibrium ARPES. On the right one is the photoexcited one. And basically what you see that there is a gap closuring between the left and right. Yeah? And the time scale for the gap closure, which they measure, is sub-femtosecond, so much faster than the lattice distortion. And from this, they concluded that this has to be electronically driven situation. However, there was a recent work by Baldini where they basically argued, repeat the same type of an experiment, but came to the opposite conclusion, basically that time scale, that the gap is extremely robust, and it does not close on the time scale of the lattice distortion. So we have kind of a problem with this classification based on the evolution of the gap. And basically what I want to propose today is let's change our mindset and introduce a new quantity to classify this, classify the competition. In particular, as I said, before I will focus on the photo-induced changes in the lifetime. Good, this is the experiment. So once again, today I'll just focus on time resolved ARPES. The experiments were done here in Vancouver in the Andrea Damascelli group. And so the left plot is the equilibrium angle resolved photo emission. You see a very nice flat band and a kink at finite momenta. And then after a photo excitation, the main thing which you see that the gap is roughly the same, but there is a very strong broadening happening in the system. Then this third plot is basically showing us the EDC, which is once again basically what you have to see, that there's a reduction of the weight and a very strong broadening, so starts to fill in the gap. Good, and there's some time evolution, and now we focus on a given snapshot in time and a given momentum point, close to this peak. Yeah. And we say, okay, let's try to understand how does the lifetime scale as a function of the photodoping. So we have in first the experiment. We're increasing the photodoping from equilibrium to larger excitation. You see that there's a strong reduction in the lifetime. There's a broadening and filling of the gap. And then the idea which we're having, let's compare this experimental observation with the theoretical approaches. And so what I did as a calculation was basically taking the model which you see before, treat electron and lattice degrees of freedom on the same footing, so it's some kind of a time-dependent GW type of an approximation, fix the gap size, but in theory, I can afford to change the ratio between the electronic or the lattice contribution of the interaction. And now we have two extreme cases, which I show. On the left-hand side are the electrons, so that if the electrons are the dominant scatterings in the system, and basically what you see is there is a very strong reduction in the weight and broadening, which is consistent with the experiment. While on the right-hand side, I'm having scattering with the lattice, and basically see that for the weakest excitation, there is almost no change in the lifetime. Yeah? So it means that there's a qualitative difference between the electronic and the lattice scatterings, and it's scaling with the photo excitation. Good. Then we come to the main plot of this talk. We can actually try to now be really quantitative. So how to estimate the quantitative ratio between the electronic and the lattice scatterings. So on the x-axis, I plot the amount of the photodoping. On the y-axis, I change what is the change in the full width half maxima of a quasi-particle. And then in the theory, I can change the ratio between the electronic and lattice interaction. So the blue curve here is the one which is really mainly for the electronic driven situation. And then we go somehow continuously to the lattice driven situation, which is the reddish lines. And what you basically see is that there is a very strong reduction in the change in the full width half maxima between the two cases. And the experimental data are now the black one. And once again, you basically see that only what you saw already on the previous slide, that only the electronic-driven case is consistent with the experiment. And that's what I now mean under quantitative estimation of the competition, in a sense that I can really now put an error bars. Okay, what is the ratio? I can put some error bars. What is the ratio between the electron and lattice interaction? What is the ratio between the electron and lattice interaction, which is still consistent with the experiment? So that's the essence. And let's go back to the Fermi liquid type of arguments, phase space arguments, to understand basically why there is such a big difference between the lattice and the electronic scatterings. Right? I'm considering a photodope insulator, and after a photoexcitation, basically you have a bunch of electrons which has cooled down to the upper edge of the valence band and created some kind of a double chemical potential, which you can imagine. But now this additional chemical potential allows us to have a bunch of new scatterings, right? It has strongly enhances the phase space for the electronic scatterings, yeah? And that's the essence of it. And if you do your math correctly, you will see that electronic change so change in the lifetime due to the electronic scatterings, it's proportional with the amount of photodoping, while scattering with the lattice, it's independent of the amount of the photodoping. It basically just depends on the Fermi-Golden rule level. It only depends on the coupling constant square times the final density of the states. And this gives us now a qualitatively different behavior between the two regimes, which now enables us to put some numbers on the ratio between the two interactions. Good. So this was now, up to now, it was some kind of a correlated semi-metals, which has some kind of some order. Now I'll try to focus state that this is not limited to semiconductors or something like that. So we can really do the same things on the correlated MOT insulators, charge transfer insulators. In particular case, I'll explain. I will show a calculation for the so-called Emery problem. So we're having d orbitals on the copper and oxygen px, py in the 2D plane. We are at half filling. And on the right, I've showed the main results. So this is like spectral function as a function of energy. The black lines corresponds to equilibrium, and the spectrum is changed. It's separated into the, let's say, upper Hubbard band, Zangre singlet, and here I'm having the p band. And the red lines are corresponding to the some delayed time after given photoexcitation. And the main thing which you have to see is basically that the spectrum is slightly shifted. This is basically what Matteo was discussing today. And on top of it, there is a very strong broadening of for instance, of the upper Hubbard band. So we're having kind of a similar situation. Let's try to repeat the same idea as we did for before on the tantalum 2 nickel selenium 5. What I plot here is the change in the spectral function with respect to equilibrium. So I choose certain delay time. I plot the difference with respect to equilibrium. The red one is the red color is the increase. The blue color is the decrease. And what you see if we just focus here on the Zangre singlet, that this band is strongly broadened once again. One can extract the lifetime of this guy and plot it as a function of photodoping. So I'm just plotting full width half maxima as a function of photodoping. And once again, you see it has a linear behavior, the same as we saw also in the semiconductor case. Yeah. But now this dependence actually measure us how strong are non-local charge fluctuations in a given system. So in more particular, this curve here, it's mostly sensitive on the interaction between the dp orbital and the non-local dd orbital, so nearest neighbor side. which means that from this we can estimate what is the importance of non-local charge fluctuation. If these are, of course, important, for instance, because they will affect your super exchange and also charge density order. So basically, we can use this as some kind of a proxy to now estimate this kind of non-local interactions. Of course, this is just a proof of principle calculation, but in the reality, what we have to add up now, it's also competition. How will the phonons change this picture? But I'm just saying that there is a rich information which we can extract from such changes in the lifetime, also in the cuprates. So, what have I told you? Basically, the main idea which I want to transmit is that the photo-induced changes in the lifetime can serve as a very sensitive measure of the microscopic interactions, and this enables us to do a quantitative estimation of the relative interaction strength. Yeah? I showed you on the example of tantalum 2 nickel selenium 5 how this can really, in combination with time-resolved ARPAs, do a quantitative estimation, and there we basically concluded that electronic interactions play a very important role. But in the second part, I really want to transmit the message that this is a very generic way to classify origin of correlated insulators, and that we can really attack the one new way to attack the old chicken and egg problem on the competing degrees of freedom. Good. With this, I would like to thank my collaborators. I collected theorists on the left, so Yuta Murakami, Riken, Andy, and Antoine are we were working together when I was at Flatiron, and with Philip and Martin, we were doing the second part on photodoped charge transfer insulators. And in particular, I would like to acknowledge the experimental work here in Vancouver, like Sydney and Fabio did great work. I mean, listening, being patient with theorists, it's not always so easy. So, and these are the collected publications these are just the publication on which this talk is based. Okay, thank you for your attention.
Thank you for the nice talk.
Thank you for this interesting talk. I am curious about the role of the VPD and the VDD.
Yeah.
Do you understand why those play an important role?
Well,
is there a simple sort of?
I think I don't have a simple answer to this. It's just, yeah. It just turns out that if you're doing if you would do such a calculation without the non-local interaction and without the non-local self-energies, the correction, the broadening, it's extremely weak. So somehow this non-local fluctuations, it's messing up, it's strongly increasing the non-local part of the self-energy. So I don't have really intuitive reason behind it, but it's basically an outcome of a calculation. Yeah.
Question. So in the extrinsic insulator case,
yeah.
If you go further high in intensity, finally you expect the gap closing?
Yes, yes.
But in that case, the broadening is more significant.
Maybe I haven't emphasized this strong enough, but the idea is really to go to weak as possible excitations to really try to address very close to the equilibrium situation, right? So we would really like to, the important thing is scaling. So this slope, not really focusing on the strong excitation. Yeah? That was the main change which we have to hear. And for this, of course, you need very nice experimental.
That's good. But can you predict the character of this photo-induced phase transition in the much higher intensity range?
So what is happening if you try to destroy the order? So what do you actually mean under character? So
like it's a first order phase transition or continuous?
So no, I think it's a second order phase transition, and basically what you expect, similar as in the typical like equilibrium phase transition. There's going to be a critical slowing down when we approach to it. But I'm not certain about the critical exponents. This is something what this you would need to extend the theory.
Okay.
So yeah,
Okay.
but second order.
So any other questions? So if not, let's thank the speaker again and thank all the